we are.
Okay. I'm going to introduce Charlie here. He's the keyboardist, a professional musician, and you have a Bachelor's of Science in Computer Science, right? And focusing on artificial intelligence. So this guy knows what he's talking about. He's not just some musician. He's a smart guy. Yeah. So you can take it away. I'd like to help direct the discussion as we go.
Well, I'm just going to talk about music and audio, and this is totally my take. First, I'm just going to say how I look at the problems associated with music, okay? So I'm going to grab a pen.
Yeah, you can erase all that. So one more.
Hold on. All right, so you've got an audio file, right? And then you've got a MIDI file. And MIDI, I'm certain you all know, it's just a version of Western musical notation. It's taking audio and thinking of it in terms of notes that start and stop, right? Which is basically what Western musical notation puts in there. And it's got a lot of other stuff that's not interesting for today, like it's got tempo and pitch change and so on. But okay, so if you've got a MIDI file, right? The information you can get out of a MIDI file, the things you can do with a MIDI file, is first you can produce helpful things for video and audio editors, right? That's totally solved. Yeah, it was solved in the mid-'80s, right? When they started Pro Tools and Avid and so on, they could take MIDI files and allow you to change the sound of music. Okay, so the next thing you might want to do, you might want to make an audio file, right? Now to make that, to take a MIDI file and play it out into audio on a computer, and to do that well, was only solved around, I'd say about 2000. And that was solved by the companies that make software instruments, right? And before 2000, there weren't software instruments that could actually convincingly produce orchestral sounds or piano sounds and so on. And now that's been solved. There is software that you can buy that will produce music that sounds good. And films that you've seen, their scores oftentimes are done using something like the Vienna Strings, which is made by Ilio, which is a plug-in. It's very expensive, but it sounds like an orchestra when you play it. Yeah, it's convincing. So this is solved. That's good. So this is MIDI to audio, right? Okay, so what else can you do? You can using MIDI information, you could run machine learning for people who want to classify audio files. That would be like Pandora or Shazam, these kind of companies. What they need is they need to know what's in that audio file up there. They need to extract features from that audio file, and then they're going to do machine learning on that and base their recommender systems on that. The MIDI data would be great for these guys, but the problem is there's not enough MIDI data. There's not enough MIDI files, so it's a sparse data problem. And the missing link is audio to MIDI, right? Now this problem is like almost solved, being solved now. There's companies that make products that do really bad, unreliable audio to MIDI, but you can't just take a Beyonce file and come back with a reliable. You might be able to get the tempo, but you won't be able to get any reliable information about the harmonically what it's like, or how exciting it is, or how any feature that you might want to extract, or the Pandora might want to extract. So this is kind of an open problem. It's like half solved. What else? Oh well, what I'm working on is using machine learning to compose music, right? And this is not solved. And I think this is what Matt's interested in, to take a MIDI file and listen to the music, listen to 500 Bach pieces, and then come out with some Bach that sounds like Bach, that's recognizable as Bach. And that I think is what Matt's going to work on. It's unsolved. We'll talk about that a little more in a minute. I want to talk about audio to MIDI a little bit, because I think this is the problem I would love one of you to work on. I'm not qualified because I don't know enough about audio signal processing, and there's a lot about audio signal processing. The reason I think that this is a good problem for NuPIC, there's several reasons. First is that there's a lot of data. There's all those audio files out there, and I can produce sets of audio file MIDI pairs. I can produce 10,000 of those by using my music generation stuff and creating audio in MIDI. This is like I have a drummer that could play for hours and hours and hours and days and days and days. And if you could turn what this drummer plays, the audio, back into the MIDI file, that would be awesome. So first of all, it's got a lot of data. There's available data for the problem. There's the space of data is kind of well behaved. It's a measure space with frequency and harmony, and it's just frequency times and time. It's a two-dimensional space that is well formed. Also, I think it's very much an early 21st century problem. A machine learning, data-based, mathematical optimization is appropriate. It's kind of like everything that everybody's working on right now. This is one of those problems. And because it's almost solved, there's a lot of papers out there, and there's work out there, and there's things that are, and the power's off. And anyway, so I think that's a good problem. I'd love to talk to somebody about that if they're interested at all.
Do you know how good the state of the art is? And if you know, let's say, let's say it's only drums,
Okay.
and it's a clean environment.
Sure. So
you go back
you can do that. In a typical recording session, you're recording a new band, and the drummer's not great, and it's really important that the drummer be great. Without a great drummer, there's no song, right? So there are plugins that you can take in, and they will find all the note onsets, map them to the different instruments that are available on the drums, and then you can sit there in Pro Tools and slide them back, or ask Pro Tools to slide them. Right, now that exists, right? So they can take an audio file, bing, and it comes out on this other track in audio files with MIDI onsets. It's basically a MIDI file. And then there's another company, Melodyne. Melodyne can take a guitar track, and turn it into the notes, but it's not very reliable. The onsets aren't great. The onsets aren't exactly right. And the thing is, with music, with at least recorded music on a high level, 5 milliseconds is a lot of time. 5 milliseconds is the difference between something seeming sluggish or seeming peppy. You can't be off by 30 milliseconds because it's going to sound out of time. It's going to sound either clumsy, or it's going to sound lazy, or it's going to sound heavy, or light, or silly. It's just, you need to get it right in that 10 millisecond window of when it was supposed to happen. And the waveform for a musical sound is kind of like, it goes like that, So you got to figure out where is the beat right there, And this is like 30 milliseconds, So you gotta pick this spot. Or sometimes it's this spot, this really, this interesting spot right here. That's where the beat started. This was the sh, and this was the pa. So anyway, so that's audio and MIDI. If anybody wants to talk about it, and I'll talk about this. Now, composition is interesting because there's several problems with it, I think, for NuPIC, and we'll see what happens. But the first one is that musical data, which is the MIDI, it's not a measure space. It's a combinatorial domain. You're talking about so we'll talk about MIDI data for a second. I need more space. So MIDI data, there's 127 notes that MIDI keeps track of, right? And then in terms of time, MIDI's in clock ticks. There's some number of clock ticks. The least you could get away with is probably 24 clock ticks per beat, right? And then that's a beat. And then events start, right? This note starts on a beat. So this right here, you get a note on message, right? And that will be associated with certain velocity, which is connected to volume. And then the note stays on for a little while, and then there's a note off message here, right? And I was going to show you guys, this is Bach's Prelude in C major, written in that form, but it's hard to see, but I can't show you. That's Prelude in C major, written just like I wrote it right there, with, that's the first movement, that's the second movement. Anyway, so you've got notes starting and stopping, and they make little regions of sound, right? So yeah, I was saying it's a combinatorial domain. So you're talking about combinations of 20. You know what I mean? So you want to ask yourself a question like, well, is this a major chord or a minor chord? Is it happy or is it sad? What's happening right here? And you know, it's a major chord if it has a certain relationship between these. It's called the intervallic relation, or the interval. You know, if these are certain integers, right? This would be 4 and this would be 3, and that's a minor chord, right? So if that means that this is a major chord, this is a minor chord, sorry. So
this is where it gets interesting, I think.
well, yeah.
Because this is where, if we're talking about encoding MIDI songs,
Right.
music.
Well, that's what we're headed to. I'm headed there. You know,
Yeah.
I'm headed where you want me to go.
Okay.
Yeah. So we want to ask if this is major or minor. That's a feature we want to take out. We want to take out whether it's mostly major or mostly minor. Yes.
Are those binary states? It's on or off, or is there like a volume?
There
scale?
is. That's the velocity number. And for me, I think it's better to have these be 0, the guys who aren't playing, right? And this guy to be his velocity, which might be 78, right?
Yeah.
And
What
this
does
is-
that mean? What does it translate to in the
Volume.
sound? Volume?
Yeah, volume. Well, it actually,
how hard to
technically
keep
it
on.
translates to intensity. So for some instruments like trumpet, you know, if you hit a trumpet hard, it's the timbre changes, right? And same with an electric guitar. If you hit it hard, the timbre's different. You know, with a like a electric organ, it doesn't matter. You know, there's a volume pedal. So MIDI has another thing for volume, but for our purposes today, I think that this is enough. You know.
Charles, do you have aftertouch? Do you use aftertouch on keyboards a lot?
I didn't.
Do you use aftertouch on keyboards a lot?
Do I use it? It's a good feature for doing string arrangements. I have used it on string arrangements because really, really high-end musical software instruments will be able to react to aftertouch
I'm just
in
thinking
various
'cause-
ways. But there's no standard there. Aftertouch can mean almost anything.
But it could vary over time
Yeah.
across the notes. Oh.
But I think we should ignore, as far as,
Yeah.
this initial conversation, everything except note on, note off.
Yeah, that's what
That's
yeah,
the important
obviously.
thing, and then we can talk about the additional features once we
I mean, there's
understand that.
lots of other features. You know, there's all these other signals which MIDI is keeping. You know, they're all digital, so they're like this. So there's like volume. There's oh geez, you know, there's 100. You know, there's reverb send. There's there's hundreds of them, and actually there's tens of thousands of them if you know how to work your MIDI. So you can run any kind of signal running along here. What he just talked about, aftertouch, is the only one of these other signals that actually goes with the note. So I don't know, you know, that you can have aftertouch and different aftertouch for different notes. So that's what makes it unique. It's note based, but that's the only one that you get that way. So I wrote, oh, he put it up here. I wrote something that takes a MIDI file and turns it into this representation. Just for now, if anybody wants to work on it, they can change it, but it goes into a NuPIC array, right? A NuPIC array that's 127 by the number of ticks. And I handled all the weird stuff, like most files have 480 ticks here, and I cut it down to 24 and handled a case where there's two things in the same tick and all that stuff, you know, all the icky stuff that can cause bugs. And so that's available. And I guess I'll take questions, or you want me to talk about more music theory?
So what I want to talk about is why it's not good enough, first of all, so everyone understands, why it's not good enough to just encode these notes as scalar values and let the scalar encoder that we already have just do its job. Because the only example that we have so far is the first one somebody did a long time ago, Pomp and Circumstance, and it worked really well, it understood the notes, but that it wasn't music. It's not, the way that it was represented was not music. And I want to understand how we can represent the difference between a major chord, a minor chord, or how the harmonics or the dissonance, how can we represent that in a sparse representation? That's what I don't understand.
Sure. These are features, right? These are features of this basic musical signal. The first thing that you were kind of talking about a little bit is voice leading. So you have a note that ends here, right? And you have another note that starts maybe here, Or it could start here, right? Now, the ear will make these into a melody, right? It goes up and down. It's scalar, like you say, it's one dimensional. So you have to solve this problem. This problem, picking the notes out of that representation to figure out what's the melody, where's the melody, it depends on a lot of factors. It depends on where you expect the melody to go, basically. And what you're paying attention to, what you're listening to. It even depends on how hard it's hit. It even depends on the
So
velocity.
that's a good point. Like when there's several notes on in a MIDI stream at one time, what's the importance? How do we rate what notes are important for the melody? How can you pick out the melody?
Well, I mean, if you do a really bad job of sucking out the top line, the
Yeah.
highest note, that won't work in general, but that will actually work for more things than you might expect. Really, it's solving the voice leading. So like the Bach's prelude and fugue there, the fugue, the second part, I can't really show you, but it's got several melodies that go like this. They generally stay in their ranges, but they occasionally do things that are weird, So it's got that, and each of these is a melody. There's 4 melodies, right? And your ear solves all these problems. And one of the magical things about Bach is that he was able to keep these so that your ear always follows all 4 melodies. If you sit and you listen for one of those 4 melodies, you can hear that one melody. And your brain, your auditory cortex is solving this problem, the voice leading problem. So that's so that even when, you've got this guy, he's jumping, Bach set it up so that your brain can solve it. I don't know where the eraser is.
It's right there.
Let's see, so 2 voices jump over each other, right? Bach's so good at it, partly because he can set up situations where your ear says, oh, that went down there, and this one went up there. Even when he's playing them on an organ where there is no distinction between these sounds. If they're singers, you could kind of hear him breathe or him swing up a little, but on a pipe organ, all you've got is the timing. Timing is your only clue that this melody went down there. So that's the whole voice lead problem. I mean, this would be the hardest problem, would be taking a 4-part fugue and turning it into 4 melodies.
So
But that's something that anybody can do instantly. Everybody can do it just sitting in front of the speaker. You can hear that one. You can hear each of the 4 melodies.
But that leads to the question of, can I do that instantly because I've heard music before, or could I do it instantly? when I
A
was
little both,
baby?
I would say. A little both, I would say, because the auditory cortex evolved to detect sound-making objects in your environment, and to divide those into separate sound sources, right? And to try to deduce the character of each sound source in the environment. So when your brain hears a 4-part fugue, it's trying to hear that as separate events coming from separate objects, which might be threatening or friendly. You know what I mean? And so that's how your brain's interpreting. Yeah.
So couldn't you gather clues by, for instance, if you're looking at 2 sources that you're trying to discern melody from harmony, one would be how frequent the notes change in both of them, because harmony tends to be less frequent in the number of notes, for one.
Right.
Harmony also tends to show up and go away, show up and go away, whereas the melody tends to stay constant. So they're like clues that you can gather from these different attributes,
right,
to discern the melody from the harmony.
Right. So if you've got somebody who's going la 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 la, you got somebody who's going this on.
Is it plugged in? You got to plug it into your.
Oh, I got to plug it back in because I turned around the computer, of course. Oh, but I also unplugged the dongle. Give that a second to think about that. So you've got one melody you've got a melody that's going, la da 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 da, right? But the chords, there's a whole other section in the orchestra, the band is going dum 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 with this chord, right? You're not going to mix up those 2 voices because here we go. Because this guy's in pop music, of course, you always have somebody doing this, and then so that way you can always separate out the voice. But still, from the computer's point of view, he's got to figure out, oh, these guys are all in the same range. They're all close to being attached at the end, but not necessarily attached. And they're doing rhythmic things which are consistent, which is what you were saying. They should also be doing kind of harmonic things that are consistent. Like, it doesn't make any sense that a melody would jump from way down here to way up there. It always jumps within a certain range, right? So there's a distribution over the possible jumps, like this, right? So this guy's doing an unusually large jump, and this guy's doing a perfectly expected jump. That's pretty normal. So we could guess that's that's what's going on. So that's the voice leading problem.
Another question when we think about encoding that keeps, comes up in other domains is what is similar? If you have, you have the minor chord there.
Right.
Could you have other patterns that look very different but actually musically similar? And how do you define similarity?
Yeah, like augmented seventh minor chords.
So
Yeah.
if a melody has some specific characteristics, couldn't you train it by removing all the other tracks?
Yeah.
And then you just train NuPIC on the melody in absence of any other sound. And so NuPIC would learn the anomalies of something that is, it would do anomaly detection on things that aren't the melody.
Right. Right.
And then maybe it'd be interesting to see what happens if you play a full recording to see if it can pull out the melody.
Right.
Right?
That's a well-formed problem. That's a good problem, and that's a good solution. That solves the voice lead
I don't know if it'll
problem.
work.
Yeah, we don't know if it'll work.
It eliminates the
But that's
voice
an
leading
approach
problem.
to solving the voice leading problem. You get a MIDI file, you don't know what the melody is, and that could be a way to figure out what makes a melody. It's also kind of machine learning-ish because you're not giving it a bunch of rules, based on classical music, like, you know what I mean? You're just saying.
A bunch of simple melodies that have no relation to each other except their melodies.
Right.
Well, that's how we learn music. Anybody who's taken an instrument starts with Twinkle, Twinkle, Little Star, right? A classical instrument.
I started with Mary Had a Little Lamb, but
Oh, snap, music burn.
well, it's the same melody.
Does MIDI encode, does MIDI give you, I'm not familiar with the MIDI
Sure.
format, but I have been a musician for a while. But does MIDI give you the hertz of
The what?
the hertz?
The frequency.
The frequency?
No, but it's easy.
But it does
It's a
distinguish.
piano note number. Imagine
Yeah, it
middle
gives
C
a note number.
is
An integer between 0 and
80
1.
hex, and if you play it back, you have to put out a certain tempo.
Yes.
Well, no, he's talking about the pitch.
Right, because Subutai's question was about encoding and similarity. So you could basically assume a key and then get the variances of each note and encode those notes, and you could determine similarity by shifting notes into the key that you're comparing, and then gathering your similarity between the notes,
Sure.
given the forced key that you're putting everything in, right?
Right.
I don't know.
Yeah, no, that's good. There is a problem that if you're going to take your MIDI files and you're going to do anything to them, if you're going to have to go through and pick out the melody, you have a data problem because you're going to have to go do that, and that's going to take a long time. You're going to get 100 done in an afternoon, and it's going to, we've already got, I brought with me several hundred MIDI files, but just digging those up and preparing them, for anything other than just, running NuPIC on them straight, it will take a lot of work.
I want to define a simple problem, and maybe it's as easy as saying we're playing something simple like Mary Had a Little Lamb, but you're playing it in chords, not in individual notes, right?
All right.
And then you hit a wrong note somewhere, so there's suddenly dissonance where there should be harmonics. That if we could identify
do
what
dissonance
encoding
in
is
concert.
required for NuPIC to identify that anomaly, that would be really useful.
Well, that's the next thing I was going to talk about was dissonance and consonance. Is that what you're thinking about?
Yeah.
Okay.
The eraser is that blue thing at the bottom.
Yeah, that's the eraser.
This is an eraser.
It looks like a spaceship.
I was mistaken. Okay, so dissonance and consonance. Okay, well, let's talk about harmonicity, right? An audio signal has harmonicity if it looks kind of like this, right? if there's a lot of energy at what's, what we musicians call the tonic, and then what we call the first harmonic and the second harmonic, right? And these are integer multiples of that. Everybody knows this, right?
No, explain this.
Everybody knows the opposite of what you just said.
What, did I just say wrong?
We don't know this.
We don't know this. Yeah.
Oh, okay.
Is this what is this? Is this
Oh, I'm
over
sorry,
time,
this is,
or
I'm sorry, this is
a
frequency.
frequency
This is the
spectrum?
frequency response
Okay.
curve. I'm sorry, frequency
Okay.
response curve through sound, right? Forgive me if I use the wrong physics name for something, so
So,
not a physicist.
low frequency on the left, higher frequency
Low
on the
frequency on the
right.
left, high
Spectrum.
frequency.
And
This
this
is what you see in
one point in time, one note struck, right? The analysis of that.
Yeah, right, so this is a wiggle. I've got it on, I had it all set up on here, but I don't think I can show it to just show some sound.
Yeah, I'm sorry, I didn't have the.
I should have asked you, yeah.
It's also the first thing your ear does.
Yeah, that's what you're doing.
Right, okay, yeah, so let's talk about harmonic sound. So, yeah, what makes a sound harmonic is that it's got these peaks in it, that represent thing. And the timbre, which is the quality of the sound, whether it's or or whatever makes the sound, that depends on how high each of these are relatively. The simplest sound is a sine wave, which looks like that, right? All the energies at the tonic, and then a square wave or a triangle wave, they have different, a square wave is all the odd numbered ones, a sawtooth wave is all of them, how much energy is spread out over these. Okay, so that's a sound that has harmonicity, okay? And, okay, so let's talk about consonants. We have another note out here, played on a similar sound, right? It's, this is an octave away, which is 12 half steps, which is this, which Chris can't hear. That's an octave. We interpret that as the same note. So here's another note at the, here it is at an octave away, right? And so what happens here is that these kind of line up. And the sum of these two is still very, very harmonic. Okay, so if you take a sound that's just very close, but not close enough to that guy, and you add these up, you get a phenomenon where the sum of these is kind of like there's these double peaks or something like that, and then there's other phenomenon going on in your ear that have to do with you perceive beats, and you're also perceiving the plus and minus frequencies of this, which are moving around with the beats, and it's theoretically it's very unpleasant, once you get really close. So the octave was consonant, and this is dissonant, right? And that has something to do with it's unpleasant for your ear to try to turn that into a harmonic sound when there's those two peaks. And like somebody just said, the whole job of the ear is to detect harmonic sounds, detect sounds that are made by, that have harmonicity. And it does this by having, by splitting it into the frequency domain, and then some method or other, somebody else probably knows how this actually works, but some method or other, it says, well, these different, I'm getting energy at all these different points, and that means that, oh, well, look, right here is a harmonic sound.
You're drawing the cochlea there.
I'm drawing the cochlea. Yes, the cochlea. Yes, sir.
Does it depend, is it a natural thing, or does it depend on the culture and the type of music and
Not this part.
That is for everybody all around the world, they perceive a dissonance.
Well, okay, now, if we define dissonance in terms of the physical sensation of dissonance, yes. If we define dissonance in terms of prohibitions or things that you want in your music or not, then no.
Okay.
Because like in jazz, of course, you can go, you can't do that, but you can do that. That's very dissonant, right?
But it sounds good.
Well, we like it, because we're used to it, right? So that depends on the culture. We're used to this sound, because we've heard it a lot, but it was almost unheard of in Baroque practice, right?
So you're defining the physical characteristic of a dissonance.
Yeah, this is a physical characteristic. Dissonance and consonance is a physical characteristic. And what I'm kind of showing you here is Helmholtz theory of dissonance and consonance, which is pretty much discredited because there's a lot of things it doesn't do, that actual experiments on people where they try to figure out whether they think a sound is consonant or dissonant. But it's kind of like this, And the best theories, and I have a couple of papers if anybody's interested, the best theories have to do with the way neurons sync up. I think make a mathematical model of neuron, I don't know what it's called, you guys probably know, but you know, when two neurons, they like to fire together and they keep firing together, they like it and they like it, and you have to perturb them a lot before they stop, you know, and so it has to do with that, and you can, there are mathematical models of that. There are better mathematical models of consonance that fit psychological experiments better. That's interested in further reading, if anybody is interested. So that's basically, consonance and dissonance in a nutshell is that that's really consonant, that's very consonant, that's also very consonant, that's not really that consonant, this is dissonant, and this is dissonant, right? And so first year music theory students, when they go in class, they take the intervals, which is, you know, all these distances, every pair of notes, and they give it, they say either it's consonant, it's unison, perfect consonants, consonants, or dissonance. 4 levels, an integer 0 to 3, that, you know, and that's all you would need to think about today. But anyway, that's some of the theory of it. Like, you can see it's a lot more complicated to actually listen to an audio signal and say, well, is it consonant or dissonant? It's actually pretty, there's some math there, but you can sum it all up in just this integer value.
I think it's definitely something that needs to be encoded. As a
How
part
does
of
it
the
map to the
system.
MIDI? How do these?
Well, you have to
Well, there
carry
you go.
out.
Okay,
right?
so
You have to manually or
so
programmatically
here
carry
in
out.
my major third, right? In my minor chord here, this is 7, right? And 7 has perfect consonants because it's an open fifth. 7 half steps is an open fifth, which is consonant, right? So you'd say if you wanted to try to figure out the consonance or dissonance of this MIDI file, the best bet for now is to you know, kind of either add these or sum these, or I mean either sum them or average them, right? You know, and try to figure out what's the total consonants happening now at this moment. So you could have a feature of this MIDI file where you're tracking the consonants. You know, that there's no consonants, and then there's whatever that comes out to, you know, and then it stops, right? So that would be a feature of the MIDI file at that point, right?
Yeah.
Talk about voice leading, we talk about consonants. Oh, I want to talk about voice leading as a feature. Because when you're talking about voice leading as a feature, you can look at the distribution of voice leading, which is kind of what I think you were talking about, which is where you can ask, once you've deduced the melody, you can ask how often, you know, does it jump, right? So you can say, well, you know, there's a 1, and then there's a 2, and then there's a 5, you know, and you could come up with a distribution. It's like, well, melodies almost always jump 1, and then, you know, sometimes they jump, you know, +2, and sometimes they jump +2, and very rarely do they jump +11, you know, or I do that backwards, -11, +11, right? So voice leading is a feature. So you can extract the feature of voice leading once you've extracted the melody, right? And that can be a signal, you know, obviously there's no voice leading in that example, but, right? What else did I want to talk about?
But we're not going to be able to know that in the middle of the MIDI stream unless we have identified the melody.
Right, so, yeah. I want to make sure I said that was a feature.
Do we have like, of the files that you have, there are some files that are like, this is a MIDI, or this is a melody only file.
Nope.
Right, I think.
What I did was grab a bunch of classical MIDI files from the classical MIDI database, because
Okay.
classical's pretty well organized. You don't worry about a drum kit in there if you're messing you up.
Yeah, so it seems like if you're actually, you know, listening to this MIDI file, you have a potential of, what, you know, many on and you know, 100 on notes possible. Yeah. How would you even structure an encoder that could possibly have
100 input.
Yeah.
Well, each one would be a single bit into the SDR, right? Every note on here would have meaning, and it would either be 1 or 0 if it's on.
And is your intuition that you would want to pre-process and like scan for, you know, interesting intervals and say, okay, among my whole set,
I don't think so. I think what you do is you set up your encoder with 128 bits, 0 to 127, and that's your cortical input into your HTM. But then you train this system exactly like you would train a child, which is you start with melody lines, and then you start adding 2 notes that make triads,
Except
right? Minor
one-
triads and major triads.
One bit doesn't represent like the octave consonants.
Right. You could do both. You could.
So you'd want to represent.
I think that's
some of those
emergent.
interesting semantic relationships between your active
Yeah,
notes.
I think you'd want to try to write an encoder that tries to match what you drew with the cochlea.
Interesting,
And
okay.
Oh.
So that, that's why I was getting to similarity.
Right.
So that sounds that sound similar will have a similar number of bits on. That's kind of the basic thing you'd want to have in an encoder
Right.
for. And it sounds
Okay.
like the cochlea is trying to do
Yeah,
that.
like a C
you
in
know?
different
Yes.
octaves is going to be very similar.
Right.
Even
Exactly.
though they're very spread apart in
Yeah.
the MIDI structure,
Right.
they're going to be coded very
There's
similar.
going to be some number of bits that says this is like a C regardless of the octave, and
Yeah.
another set of bits that might talk about which octave it is or something.
Yeah,
You know,
right,
and
yeah.
That way you can just think about both independently.
Okay, yeah, I should have mentioned this
Like
earlier.
encoding
but,
gates.
Let's talk about pitch class. Okay, so, these are all the notes with all their numbers. And then you've got, this is a C, and this is a C, and this is a D, and that's a D. So there are 12 pitch classes, right? And some people, put these in a spiral, so that you've got here's the C, and there's the C below. And there's definitely things that depend, that if you take this song and you rotate it, right, you get something that most people couldn't tell is different. If you rotate it a little bit, almost no one can tell that it's different.
You're talking about playing it in a different key?
Yeah.
That's all the key is.
Yeah, if you play something, if I change it a little bit, you probably, if I hadn't started with the 1, you would have never known I was doing anything different, right? And, so that's called transposing, but, so for every note, there's a function which gives you the pitch class, which is basically you just mod it by 12, and that gives you the pitch class. So, pitch class of C is 0, and D is, C sharp is 1, and B is 2, and so on, right? So, you could take a MIDI file and you could say, what pitch classes are here? And that would be another signal that's, also interesting. What pitch classes am I looking at?
But you'd
And
have to
then-
do it over time, right? You couldn't take one instance in time and all the notes on and identify the pitch class.
Oh, yeah, no, you
You
could. You could, right. You just say, this is, I'm trying to do one that's easy. This is, nobody plays this time, but this is 120. And, obviously the octave is 10, right? And the pitch class is 0, so it's a C, right? It's a C in the 10th octave of MIDI, right? I actually put a little function that does that, but it's trivial. It's just mod 12, But there's interesting information also this way. You can't reduce it.
Yeah.
You can't reduce it to pitch classes because you need to know, like just for these jumps, you need to know that this guy was here, not here. This is 12 below him, say. You know what I mean? Those are different things. They're similar, but different. So like, if I take a voicing like this, and I switch that top one down an octave, you get something that has a different quality, but it's still the same chord. It's still the same chord. Still it's the same thing along some dimension. So it's the same thing in the pitch class sticks. Yes.
So there's a lot of different features that you could look at.
Yeah.
At any moment in time, let's say there's a snapshot in a song, you hear that, and then you hear another snapshot later in the same song or a different song. Trying to figure out whether they're really similar or really different, and trying to characterize that. What are the most important features, according to you, of what would determine how similar those two sections are of the song at moments in time?
That's a really excellent question. I mean, that is kind of the question.
Yes.
So that is and I don't have an easy answer. I'd be faking it if I did.
Even the chord system doesn't have an easy answer.
What's that?
This has to do with sampling other people's music, and like even the chords have tried to figure out,
No, but like
are
you
they
have
similar?
You have two
No,
Bach
he's asking
two
what-
Bach pieces sound very similar, but Bach and Beethoven might sound
So-
very different.
He's asking what is the short list of essential features to really capture the nature of a song to be able to produce something that sounds good, right?
I see.
That's kind of like that's like the whole thing. That's like an excellent question. Like, if we knew that, we could just extract those features and use traditional, you know what I mean?
It's easy, it's the temporal pool classes, SDR bits corresponding to each of the songs, and you look at the overlap. That's yeah, it's pretty easy.
Yeah,
It's all in the SDR.
So as soon as we solve this problem, we'll have solved the problem.
Yeah.
Yeah, exactly, right.
Could you
Excellent question.
Sure.
I'm sorry, you had one back there. Didn't you? Somebody did.
Could you take advantage of the way the music's laid out, the chord structure, the difference between those, the relative information,
Right.
as you were?
Well, okay. Yes, we talked about pulling consonants out. As far as asking, is it a major or minor chord, like who's there, what's going on, you're in a combinatorial domain, right? And even if you cut it down to the pitch classes, suppose what's playing now, here's the pitch classes, there's 12 of them, right? So what's playing right now is this, which is a C major triad, right? It's a C major chord, it's this. Right? So that's playing right now. But that's one of, 4,096 possible things that could be happening right now in pitch class space. Is that right? Somebody check. 2 to the 12. Yeah, you were talking about, you've got several things going on here, and we want to know if this has happened again in a piece, or classify these.
You're not going to get all the combinations, like combinational space. You're not going to fill it. All the music
Right,
isn't going
it's
to fill it. It's
very
only
stated,
like
right.
small, because of we like the certain differences between those.
Right.
So the 4,000 is a lot smaller.
Oh.
If you see what I mean.
We don't tend to play.
You've already got a certain number of fingers and stretch, as it were, to try
Right.
and play these notes.
So yeah, you can cut the space down considerably, but in our age of big computers and so on, the space is already pretty small. For machine learning, 4,096 is not a big number, of possibilities of a range for space to happen.
I think the main thing I'm trying to convey is getting the difference between the notes. So going through a difference. So you get the first
I
note
see
and then
what
there's
you're
a difference. So
saying.
you've got the fours and
So the
threes.
delta,
intervals rather
the
than
delta of the note
So
numbers.
encoding the intervals between.
Right. So we have 3 notes, N1, N2, and N3, right? And so what we actually look at is N3 minus N2, right?
Yeah.
N2 minus N1, right? Just look at the intervals.
Yeah.
Are you talking about simultaneous notes being played or over time?
Simultaneous notes being played.
Like a chord?
Yeah.
Yeah.
Yeah. And
And
encoding the
encoding-
difference between
encoding
them
that
somehow,
difference, yeah.
which would be like the range of the notes that are currently on.
No, it would actually record the pattern,
Yeah, not just the.
regardless
time.
of where it's moved up and down. It would collapse the
Yeah.
space
Right.
so that all patterns that are just something moved up and down would be
The only awkward thing is you might need to define the tonic.
the tonic of the key.
Of
that consonant, it's like there's dissonant energy in C versus dissonant energy in E. That would you would want to know the difference there.
Right. Well, that brings up another thing, which is that, obviously there's a lot of structure in a musical piece. For example, a composer has chosen a scale. He's chosen a particular chord for a particular, small part of the music. I think everybody probably knows what these are. They're subsets of the set of notes. And this is a subset of the set of pitch classes, right? It's like usually there's 7, might be 8 or 6. And then the chord is, some subset of that, right? So these are features of the signal. Part of the scale is that each scale has a tonic. Each chord has a tonic. So altogether, the harmony, what musicians call the harmony of a particular bar or a section of a piece, involves 2 numbers and 2 sets over the pitch classes, right?
Where does key fit into this?
This is the key.
The tonic is the key? Okay.
This is the key, right? Which you also call the tonic of the scale. Sorry, there's 10 words for everything. Right, there's a key. So, you know, at a certain part in, you know, the beginning of that piece, we already know that the tonic is C, you know, the first chord is C major, right, and the scale is E, right, right. If it was an A minor, you know, I feel like I'm not explaining this very well. But this is the same. Okay, so A minor, this scale is the same notes. It's the same subset of the pitch classes with a different note chosen as
The starting point?
key,
Or the
as
key?
the key, right? The key. I like the key.
So were you saying like the intervals between the notes of the scale are the same, they're just shifted? Or
Well, no,
is
these are the
that-
same pitch classes in A minor. There's several minor scales, but this A minor. That A minor is the same pitch classes as. It's the same pitch classes. The only difference is I approach the chords in it differently because it's A minor and this is C major. Does that make any sense? I'm sorry.
The key signature is the same,
I
there's
can
no
explain
sharps or
it better.
flats.
Okay, but the point I wanted to make, and this is the most important point, is that this is a hidden variable, right? It's not in the notes you're seeing. You know, it's not there. Nobody's written it out for you. And in fact, commercial MIDI files you can, when you download 1,000 MIDI files off the net, it's not reliable. It might be wrong. It's wrong a lot, you know? And especially because in a real musical piece, the composer's going to be shifting keys. You know, he's going to shift keys on the thing, and he might not bother to tell MIDI that he's shifting keys, and just use, you know, different notations to let you know it's different. So,
You said this is a hidden variable. Did you mean key?
the harmony, yeah, the key, the scale, the tonic of the chord, and the chord.
So all the data in the harmony is hidden variable.
It's a hidden variable. It's all a hidden variable. Because all you see in the file are these. You see the notes, right? And so,
And that's the thing our encoding has to represent somehow. Are these hidden values in the music? Down in the,
if you want to represent, also it should be said, this is Western music, too. This is Western music. This is not brain-based. We talked about that earlier. This has nothing to do with the brain. This has to do with Western culture, right? This is how Western musicians organize their music in terms of key, scale, chord. That's how they do the harmony. So if you assume you're doing a Western piece, then a lot of music uses keys, but only Western music really uses chords the way it does.
But when you're listening to it, you can tell the difference when it's changed.
Oh yeah,
You
can tell it instantly. Yeah, that's partly cultural.
Yeah, there's a learned thing.
But nobody had to train you. Nobody had to say, the chord's changing now, Charlie, little Charlie. You know, nobody did that while you were listening to music. Nobody taught you to listen to, hear the chord changes, but we can all hear it. But that's because, I don't know, and I want to say what the other hidden variable is, which is also important, is I think I should talk about meter, because I think we're almost done. I probably scared everybody off of working on this at all.
music theory is a bit like alchemy.
Is it?
To me,
I mean, it's pretty simple. It's just combinatorics on you know, a
I
space
think
like
it's
this.
just unfamiliar.
Yeah. I mean, this is just a subset and a subset of a subset.
Yeah.
And then a particular guy chosen to be special, and then another guy chosen to be special. It's just it's not that complicated. And how many other ways would you take all the notes and cut them down? One thing that we're seeing in music theory that's interesting is that music theory is something that you teach to human musicians, right? So everything in music theory has small numbers of things, right? Humans can't remember 4,096 combinations. We can't organize 4,096 combinations in a way that makes any sense to us. We have to divide it into, there's one major scale, there's only one, and there's 3 minor scales that are popular, 2 other scales that are used in jazz, and that's it. We only have 8 scales, 8 or 9, maybe 12 scales if you counted every weird scale, right? Chords, they're either major or they're minor, and then they have extensions. So when you're teaching people chords, you're really only dealing with like twos and threes, very, very small numbers, you know. But the reason that is, it's not a feature of the space. That's a feature of teaching music to humans. Does that make sense? So maybe we need to show these to NuPIC, maybe we don't.
I think
Right?
we know.
We have to decide, are we going to make a universal encoder or a cultural bias encoder?
Well, yeah,
Specifically
as soon as you
bias.
put the culture in there too much, you start just generating random cases in the culture, which actually sounds pretty good. You know, I don't know if any of you ever heard the ELIAC suite, which was made in the 50s on machines with absolutely no power. But you know, he just took a couple of features here and randomly chose between them. It sounds great. You know, it's really interesting, beautiful music. And you know, you could do that without any learning, without any, you know, so it doesn't take much if you restrict the space enough to come up with music that sounds pretty darn good.
Yeah, I mean, it seems to me like if you could come up with a basic encoder for music that encodes all the basic characteristics, and then you play a lot of Western music, it should be able to learn, you know, bits that correspond to these different variables.
Right. Well, I think meter is another key thing that we got to talk about.
Can I ask?
Yeah, sorry.
Can I ask/say something?
Say something.
Here's the way I would approach it. So I would have a composite encoder, just like you do with your date encoder. And the composite encoder, you would have a scalar value for each part. You would have like the attack of the note, the actual note, the duration of the note, the timbre of the note. And you start with this just the small things, and you're able to quantify, you know, just exactly what the important qualities of a note are. And each sub-encoder inside of the parent encoder would be responsible for its range of bits that encodes this quality. So you would have, you know, 5, 6 qualities. Start real small. And this composite encoder, each encoder, the scalar encoder inside, would be responsible for characterizing that part of the note. And then once you're able to encode this and you can put it into the HTM, and you can play notes, and it can predict notes based on, you know, it can predict notes, then it might not be necessary to try to quantify exactly what a key is, because given you know what it's already working with, it can kind of infer the key because it's going to only predict things that are, you know, that it's seen before, and things that are, you know, relevant to the key that it's already been working in, kind of like that. So I mean.
Well, you said a composite encoder, but then you only explained one of the composites.
No.
Right?
No, you have the note.
That's one.
C,
Right.
A, B, A, B,
Yeah.
C, D, E,
Right,
F.
the attack.
The qualities of the notes.
And then the attack of the note,
But that's
hard,
still
soft, whatever kind of way. Then you have the duration of the note.
Well, we
you
can't
have
do
the
duration
timbre.
because this is a stream.
Huh?
We won't know the duration if we're streaming this, right? It's going to be at any point in time in a musical stream.
I would say you sample it.
We could get the duration.
Take 5 millisecond samples, boom, boom,
Okay.
boom, boom. And how is it changing over that 5 milliseconds? Boom, boom, boom. Or I don't have any idea of
Is
the exact
the
number
timbre
of
kind
milliseconds.
of built into what your velocity measure is? Is that kind of what's
MIDI
in the
doesn't
timbre?
record to a timbre. That's up to the software instrument.
Because that's all the attack and decay stuff would have to be what you're talking about, right? The whole
Right.
whole envelope.
Well, I'm talking about just trying to get a lot of quality out of it. But
Yeah.
I mean, you start simple though. Just see how it works with.
Yeah, I mean, just starting with this is the chord, not the chord, excuse me, the note, like
This is the note.
1 through 12, right?
Yeah, but the note seems easy.
Not 1 through 128.
It's a
1 through
combination
12.
of MIDI notes. That's the hard thing.
Well, here's
you
here's
have
how I
multiple
would
bits
pick
on
that.
with multiple
Here's
notes
how I
on
would
it.
pick that. Make a grid of notes A through G, or 12 notes, and then 10 octaves. You have 120, and then like if you shift key, and you just say, you know, what kind of energy do I have in each of those cells? If I shift key, that's a motion up or down. If you know, and then you can think of it like a vision problem. You know, recognizing the shape of something, whether
Oh,
whether a
okay,
normal
sorry.
song yields a kind of coherent shape,
for.
Right.
With that,
You're talking about-
concentration, I don't know.
Well, that would be
Topology
that
of
shape changing
the-
concept.
He's talking about topology.
Yeah.
Use
Which
use
is
a
a
multi
multi cortex, and you have
Yeah.
topology, it's treated like a vision problem.
use a multi-encoder for your composite encoder.
Yeah, that's kind of like the voice leading problem is topological. You're trying to follow this guy, you're trying to watch this guy, and the guy's the melody, right? And you're watching in this
Yeah, yeah.
0 to 127 space, right? You know, so yeah.
Hey Matt,
You
why
wanna talk about
why
meter?
do you think?
I got to talk about
Yeah,
meter.
let's-
Let me talk about meter,
I know you have-
and then, because it's the clue to the hidden variables is meter. That's why we have to talk about it. Okay, so time, right? Time in music depends on what I believe is our innate sense of a beat. I believe that built into our cerebellum is a machine that, down to like in the 5 millisecond range, can match a beat, right? Really powerful machine back there, and it dictates a lot of what happens in music. In all musics, in all cultures, there's this. Well, there's some say so never mind. But if it has a beat, you know, they all have. A lot of music has beats. I'll say a lot. Has beats, right? And so you start with the beat, right? And then in most music, then you group them into larger units, right? Right? And you subdivide them into smaller units, right?
You're off by 1 on that first bar.
Oh, thank you. I was trying to do 4. I'm off by 1 up here. Thought I had 8, but I didn't. Or I need 9 decibels. So, right? So, in the MIDI file over there, things happen here. They happen. This is called the bar, or the measure. This is the beat, right? And this is the 8th note. Sorry, there's not a better name for that. Sorry, my writing's so scrambled. So this is the beginning of a bar, which we call the downbeat. Things happen there. Notes start there. Keys change there. Chords change there. All the change happens right there, right? And then there's less change. There's almost never any change there. Like that's an insignificant place, right? Sometimes change happens here. You know, that's pretty interesting. That's, you know, and then up here, you know, I have another layer. You know, stuff happens here, right? And the hierarchy goes on up to sections, movements, you know, and it goes down to smaller units, which are called, you know, 16ths, 32nds, 64ths, right? Okay. So that's the basic layout of Western music and most other music. There are ways that we trick this system by running 2 meters at once. None of that's important right now. It's really prevalent in African music. It's also, you know, we have syncopation and other things in our music. But anyway, so basically, let's just look at it this way. Okay, so if you look at the number of things, like there's 4 beats per bar, right? Beats per bar, and there's 2 8ths per beat, right? And then there's almost always 2 16ths. That's the meter, the ratio, right, in this hierarchy. How many ticks you get going down low? Yeah.
Is 1/64th in MIDI terms the smallest
resolution?
Yes.
Right, well, I'm getting that. The thing here, this is called a tick, right? And it's the lowest, the fastest resolution in the MIDI file. And like I say, it's typically 480 ticks per beat. On the composition side, it's usually 24 ticks per beat. You know, on the other side, if you're generating music, you tend to use 24.
Do you need a tempo to actually tempo involved?
Right, there's tempo. Okay, so tempo, so we got meter, that's meter, how it's structured hierarchically. And then the other element in time is tempo, which is basically a function from the beats to time. So if you have a tempo, the tempo guy, you know, with a little multiplication, very obvious multiplication, you can find out what time this occurs, right? So you've got this, so right down here at the bottom, we got clock ticks, tick, 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 tick. So using the tempo, you can take this tick, and you can say, what time is that tick going to occur relative to the beginning of the piece? You know, and you can get it in milliseconds or nanoseconds and say, you know, so tempo is basically a function from ticks to beat. of time. And you can also take time, and with a little multiplication and a floor or a round, you know, you can get back to a tick, right? Okay, so the tempo and the meter are also hidden variables, right? We get the clock ticks in MIDI, so for all the MIDI files that I have examples for, you don't have to worry about tempo, because the MIDI file encodes the tempo, and that's fine. There are MIDI files out there that don't encode the tempo, they encode the seconds, actually the SMPTE, if you've ever heard of that, a certain way of looking at the time that they use in film.
I don't think we should depend on it having a tempo. But
I think you have to.
you do?
Well,
what if we're...
deducing the tempo is very hard work. It's a hidden variable.
Or maybe I'm not saying tempo, the timing.
You mean the
Per
meter?
minute.
Yeah, yeah. Like you said, we've got all these ticks. I mean, we're going to want to be like predicting when the next beat is going to come based on the music we've seen.
Right, so you're looking for ticks per beat.
Yeah, something like that.
Right? And that's recorded in the MIDI file.
Yeah, that's an invisible variable, right?
No, this you've got. You've got this. You've got ticks per beat. Every MIDI file has ticks per beat. And I wrote up here on GitHub. I wrote a little thing to take a MIDI file and switch it into 24 ticks per beat, which saves you a lot of hassle, and also gets rid of you know, when two events happen on the same tick, and you know, anything else that's weird. Yeah, ticks per beat is sort of the first level.
I'm thinking of, I think there's a lot of interesting applications if we could, for live music, for playing live music, and then you're not going to have that because of the human element involved.
Yeah, well, that's true. I mean, that's kind of like the real problem I want everybody to solve is audio to MIDI, and you got to deduce the tempo, and that's like the first job. Because as soon as you deduce the tempo, everything else becomes a lot easier, because if you're asking, like, you want to figure out what the key is, when the key changes, you know, knowing, I call this the beat strength, right? The strength of a moment of time, which goes kind of like this, right? You know, it goes, you know what I mean? So that there's this point of time, things happen there. Notice changes happen here, right? Changes happen on beat, and certain kinds of changes happen here, certain kinds of changes happen here, you know what I mean? And the relationship beat strength to time is really important. So, you know, to deduce key, you know, you want to find key given, you know, or key change, you know, the key change, given that there's a key change on the beat, and it helps a lot. It helps a lot with everything. If you're doing audio to MIDI, it helps you to deduce, you know, whether the note is changing, and if there's a lot of slurry sound in there, you want to say, well, it probably was intended to change on the beat right there.
Yeah.
If you know what the beat is.
It really constrains the problem.
Yeah. Yeah. I don't think it's tractable. You know, there's just too many possible choices for key, too many possible choices for meter. You know, that all might kind of work. Not at all.
So I don't want to rush you, but I know you have to leave.
I do have to leave.
It's 1:30.
Yeah.
Just letting you know.
I mean, that's sort of an introduction to some of the problems, you know.
That's fantastic.
Yeah.
What is in the
Like I said, the thing that opens a MIDI file, it could get the pitch class.
You got that little NuPIC, has a NuPIC.
Yeah, it's a NuPIC. I mean, you could modify that code to stream it if you want to stream it somewhere. Solves all the icky problems. MIDI's really icky, you know, it's ancient and it's been built onto, and you know what I mean? It's really like, you have to split, you know, nibbles, split things into nibbles and variable length numbers, and you know, it's pretty ugly. Yeah, I think that's all I got, unless I'm forgetting something.
Well, thank you a lot.
Yeah.